simple harmonic motion, and circular motion. The motion of a body is said to be simple harmonic if 1. The acceleration of the object is directed to a fixed point. 2. The acceleration of the object is directly proportional to the displacement from the fixed point. Examples of simple harmonic motion are oscillation of the simple pendulum, vertical oscillation of a loaded spiral spring, motion of the car wiper, etc. Circular motion occurs when a body maintains the same distance from a fixed point at different positions. Such a body moves at constant speed in different directions. Simple harmonic motion and circular motion are described with the following terms: frequency, amplitude, period, angular frequency or angular velocity, angular acceleration, etc. For circular motion, a force called centripetal force keeps the object moving along the circular path. This force is directed to the center of the circle. The centripetal force is the product of the mass of the object and its centripetal acceleration. By this we mean centripetal force is equal to mass times acceleration, where m represents the mass of the object, small letter a, the acceleration of the object. Description of the terms. 1. Frequency is the number of complete oscillations made per second. In formular terms, frequency is equal to number of complete oscillations or revolutions divided by the time taken to complete the oscillations. Frequency is equal to the number of oscillations divided by the time taken to complete the oscillations. The unit of frequency is the hertz. Then amplitude is the maximum displacement of the object from its rest or equilibrium position. Period is the time taken to complete a cycle of oscillations. Period is equal to time taken to complete oscillations divided by number of completed oscillations. Period is represented by capital letter T is equal to the time taken to complete oscillations divided by the number of completed oscillations. The unit of period is the second. The period is the reciprocal of the frequency, meaning period is equal to 1 over frequency, or frequency is equal to 1 divided by the period. Also, angular velocity is given by the formula omega is equal to 2 pi f, where f is the frequency, or 2 pi divided by period, capital letter T. Angular velocity or frequency is related to the linear velocity as follows. Angular velocity is equal to linear velocity divided by the radius, where omega represents the angular velocity. V is equal to the linear velocity. R is equal to the radius. Also, acceleration A is given by A equal to the square of the angular velocity times the radius, or acceleration is equal to the linear velocity squared divided by the radius. When a body is carrying out simple harmonic motion, energy changes takes place. For an oscillating simple pendulum, the energy keeps changing from potential energy to kinetic energy and vice versa. This is an illustration of the oscillation of the simple pendulum. At position A, it has maximum potential energy. As the bulb moves from A to B, from here to here, the potential energy decreases while the kinetic energy increases. Increase in kinetic energy means the velocity increases. At the equilibrium position, at this center point here, also called the rest position, the bulb has maximum kinetic energy. That means the velocity is at maximum, and the potential energy is zero. Finally, as it moves from B to C, from this position to this position, the kinetic energy reduces and the potential energy increases. At position C, it has maximum potential energy and zero kinetic energy. The period of oscillation of a simple pendulum depends only on the length of the string and the acceleration due to gravity. The relationship is given by this equation. Period is equal to 2 pi square root of the length divided by acceleration due to gravity. For an oscillating loaded spiral spring, the period is given by capital letter T is equal to 2 pi square root of m divided by little k, where m represents the mass of the load on the spring, k is equal to the force constant of the spring. Example 1. If a wheel 1.2 meter in diameter rotates at 1 revolution per second, calculate the velocity of the wheel. Option A, 3.6 meter per second. Option B, 3.8 meter per second. C, 4.0 meter per second. Option D, 7.5 meters per second. The solution is as follows. Solution. From the question, we are given the diameter of the wheel. Diameter B as 1.2 meters. This implies that the radius r, which is diameter over 2, is given by 1.2 divided by 2, 0.6 meters. Also, we are given the frequency. We are told that it moves at 1 revolution per second. Frequency is 1 hertz. That's the implication. Therefore, we can get the velocity by remembering that velocity is equal to the angular frequency times the radius. Velocity is 2 pi f, that's for the angular frequency, times the radius. So we have V is equal to 2 times 3.14 times 1 times 0.6. The velocity will give us 3.8 meter per second. Option B is therefore correct. Example 2. A simple pendulum 0.6 meter long has a period of 1.5 seconds. What is the period of a similar pendulum 0.4 meters long in the same location? Option A, 0.71 seconds. B, 1.22 seconds. C, 1.25 seconds. D, 2.00 seconds. The solution is as follows. The period of an oscillating simple pendulum is related to its length by the equation. The period T, 2 pi square root of L over G. From this equation, it's clear that the period T is directly proportional to the square root of the length. T is equal to a constant times the square root of the length. This implies that T1, T divided by the square root of the length is always constant. So the period T1 at a given length L1 is equal to the period T2 at another length L2. From this, we get to know that T1 divided by T2 should give us square root of L1 over L2. This is the key equation we are going to use to solve the problem. We are given the period as 1.5. That's the first period. We are looking for the second one. We are told that the length is 0.6 at that time, at that period 1.5 seconds. L2 is 0.4. If you divide that, you will get square root of 1.5. Therefore, T2 will give you 1.5 divided by square root of 1.5. The needed period T2 is equal to 1.22 seconds. Therefore, option B is correct. Example 3. A gramophone record takes 5 seconds to reach its constant angular velocity of 4 pi radian per second from rest. Find its constant angular acceleration. Option A, 0.8 pi radian per second squared. B, 20.0 pi radian per second squared. C, 24.0 pi radian per second squared. And D, 24.8 pi radian per second square. The solution. The angular velocity was given. Angular velocity was given as 4 pi radian per second. Also, the time was given as 5 seconds. We are asked to find the angular acceleration. Angular acceleration is given by angular velocity divided by the time taken. This will give us this over time, and that's 4 pi divided by 5 in radian per second square. So the angular acceleration is 0.8 pi radian per second square. Option A is correct. Example 4. A simple pendulum of mass m moves along an arc of a circle radius r in a vertical plane, as shown in the figure below. What is the work done by gravity in the downward swing through the angle theta to 0 degree? Option A, mgr sine theta. B, mgr bracket 1 minus cos theta. C, mgr. D, mgr bracket 1 sine theta bracket close. The work done by gravity, represented by letter W, is equal to the force times the distance covered. This work done is obtained by taking the two factors necessary, that's the force and the distance, separately. The force is equal to the weight of the object. Weight of object, the force is mg. Then to get the distance covered by the swinging pendulum, we take the portion represented in the diagram. The distance expected is the distance from the equilibrium position to the new position of the ball. This is the distance we need. This is the angle given. And of course, we know the radius. We can use our knowledge of mathematics. This is a right angle triangle. We are looking for this theta, this radius. Therefore, the opposites being the distance divided by the hypotenuse will give us the sine of the angle. This means the expected distance is equal to the radius times the sine of the angle of swing. With these two informations, the expected work done is therefore equal to, which is FD, is therefore equal to F is mg times the distance r sine theta. Option A is correct.